At their core, large language models are optimized for a single statistical task: autoregressive next token prediction. They ingest massive datasets of raw web text and adjust their parameters to minimize perplexity, calculating the most probable next word in a sequence. But predicting the most statistically likely continuation of a text prompt does not guarantee a safe, truthful, or helpful response. If a user asks a question, the model might answer it, but it is equally likely to generate a list of similar questions, mimic toxic internet arguments, or output entirely fabricated information. This chart compares the physical scale of the massive 175 billion parameter GPT-3 alongside the 100 times smaller 1.3 billion parameter InstructGPT model. The superimposed line graph shows a clear, counterintuitive result. In blind evaluations, human judges overwhelmingly prefer the outputs of the smaller InstructGPT model. The smaller model consistently wins because its weights are no longer optimized for statistical probability. It has been explicitly trained to follow the user's instructions. Achieving this level of behavioral alignment requires stepping away from the pure pre-training objective. We have to replace next token prediction with a mathematically rigorous proxy for human preference. To bridge this gap, the InstructGPT paper outlines a framework known as Reinforcement Learning from Human Feedback, or RLHF. The core technical challenge of RLHF is translation. We need to take the highly qualitative, ambiguous concept of what a human prefers and convert it into a scalable, differentiable mathematical objective that a neural network can actually optimize against. The researchers engineered a solution in 3 sequential stages: supervised fine-tuning, training a reward model, and finally, proximal policy optimization. These 3 stages operate as a continuous, interdependent pipeline. Each subsequent phase is specifically designed to correct the physical and computational failure modes of the step that came before it. The pipeline begins with data collection. Researchers hired human labelers to manually write out approximately 13,000 ideal responses to a diverse set of prompts, creating a high-quality demonstration dataset. This data is fed directly into the base GPT-3 architecture. By training the model on these human-written examples, the system generates our initial supervised policy. Looking at the specific mathematics here, this stage relies on standard autoregressive cross-entropy loss. The model is simply updating its weights to clone the exact behaviors and word choices found in the human demonstrations. But this approach hits an immediate bottleneck: the physical constraints of human layman. Writing thousands of lengthy, perfectly formatted responses is painstakingly slow and prohibitively expensive. We cannot generate enough manual data to continuously train and refine a highly capable language model. For the alignment pipeline to scale, we have to transition away from humans actively writing the text and build a system that can automatically evaluate the text the model generates on its own. This brings us to stage 2, the reward model. The goal here is to construct a proxy evaluator that can score the language model's outputs without requiring continuous human intervention. To build this, we take a copy of the model we just fine-tuned. We strip away the final token prediction layer, the part that guesses the next word, and replace it with a scalar output head. Now, instead of generating text, the model processes a prompt and a response and outputs a single numerical score. Next, we change how we gather human data. The system presents a human labeler with a single prompt and several different candidate responses generated by the model, usually between 4 and 9. The human simply ranks them from best to worst. This ranking mechanism relies on a highly efficient combinatorial property. By asking a human to rank just 9 completions, we don't get 9 data points. We get 36 distinct pairwise comparisons of a specific winner versus a specific loser.
These pairs are fed into the reward model using the pairwise Bradley-Terry logistic loss function. The model updates its internal parameters to maximize the log likelihood that the scalar reward assigned to the human preferred response is mathematically greater than the reward assigned to the losing response. By swapping text generation for comparative ranking, the reward model solves the human labor bottleneck. It compresses tedious manual writing into a highly scalable mathematical signal that scores human preference. With an automated scoring system in place, we reach stage 3. Here, we apply Proximal Policy Optimization, or PPO, to update the language model using our new scalar reward. The architecture for this stage runs 2 models in parallel, a frozen copy of our original fine-tuned model, and a new active reinforcement learning policy. Both models evaluate the same prompts, and the active policy's outputs are judged by the reward model. But optimizing a neural network against a static mathematical proxy introduces a catastrophic risk known as reward hacking. If left unchecked, the active policy will rapidly discover mathematical loopholes in the reward model. It will learn to output nonsensical gibberish that somehow triggers massive scores, completely abandoning coherent language in pursuit of infinite points. To prevent this exploitation, researchers engineered a constraint using the Kullback-Leibler, or KL, divergence penalty. As the active policy updates to maximize its score, the KL penalty measures how far its output distribution drifts from the frozen, human-validated model. If the active policy strays too far into strange, hacked linguistic territory, the penalty subtracts from its reward. The KL divergence penalty acts as the essential governor of the system. It allows the model to continuously optimize for human preference, while strictly maintaining its fundamental linguistic coherence. While this pipeline successfully aligns the model's behavior, the researchers documented a severe hidden cost to the process, termed the alignment tax. This graph tracks the model's performance on traditional natural language processing benchmarks over time. When the policy is optimized strictly for helpful chat preferences, its competence on standard reading comprehension and logic tests drops sharply. To rescue the model's baseline intelligence, the engineering team developed a targeted fix called PPO-ptx. By actively mixing gradients from the original, broad internet pre-training distribution back into the PPO loss function, the performance regression is halted, and the benchmark scores recover. The alignment tax forces a structural compromise. Generating an aligned assistant requires actively refreshing the model's broad world knowledge during the final stages of fine-tuning, ensuring it doesn't forget how to read while learning how to chat. The final results of this architecture are stark. On actual API prompt distributions, the 175 billion parameter InstructGPT model beats the unaligned GPT-3 model of the exact same size 85% of the time. It also outperforms models fine-tuned exclusively on academic datasets, though by a slightly narrower margin. This gap exists because real users do not typically interact with models like an academic exam. 57% of API requests are open-ended generation and brainstorming tasks. Traditional benchmarks fail to measure this specific, highly subjective utility. However, evaluating the final model also requires cataloging its remaining flaws. Even after the complete RLHF pipeline, the model still commits simple logic errors. It directly reflects the demographic biases of the contracted human labelers, and it remains vulnerable to adversarial jailbreaks that force it to output harmful content. The 3-stage architecture successfully translates qualitative human intent into a scalable mathematical objective. But the lingering failure modes show that alignment is an ongoing optimization challenge, constantly requiring new constraints to manage an inherently unpredictable statistical system.